We've talked about wind and rivers and their erosive capabilities, but none of them are as powerful as glaciers. Obviously, glaciers are a large mass of ice that's stored on the land. So one thing to know is 77% of the world's fresh water is actually frozen ice. And so most of the fresh water on Earth's surface is not rivers, not lakes, but actually stored on the land in the form of glaciers. Where we're going to find them, we're going to find in two key areas: high latitudes or polar areas, places that have a latitude close to 90, but also places that have high altitudes. Key idea there is for us to have ice, obviously we need bitterly cold temperatures, and so this relates to weather and climate ideas. Where we're going to find them, we're going to find them in Antarctica and Greenland, or the highland, more mountainous areas like the Rocky Mountains and the Himalayas that are quite tall mountains that poke up quite high. Two key places where we're going to find glaciers. Another key characteristic of glaciers is they form, or their glacial boundary, let's say, is what we call the snow line. Simply put, that's the latitude or the elevation that winter snow can last the entire year through the summer and back into the winter. And so this is essentially when the glacier, the kind of the edge of it, where the glacier remains ice for the entire year. One characteristic is currently the world's glaciers are actually retreating. So what that means is glaciers are actually shrinking. Now this could be or could not be because of what we would refer to as human-caused global warming, but we know no doubt that glaciers over time have had these periods of advancing and retreating way before humans were here. And this is note, and we'll flesh this out a little bit later on. The main contributor to understanding why sea level is rising currently is the fact that glaciers are melting. These glaciers, and so essentially you have water that's stored on the surface on land in the form of ice, is of course now melting and running off and going into our oceans, causing the sea level to rise. The photo on the top is from 1914, the photo on the bottom is from 2009, taken from the same exact vantage point. And you'll note that you can see the retreating glaciers in this comparison. If global sea level would rise just 1 meter, or about 3 feet, the areas in red would be underwater, indicating the vulnerabilities much of the United States is, especially where our densely populated areas are, along these coastlines to global sea level rise. Same idea, but for Florida. And then finally the Louisiana coastline. This relates this to plate tectonics, and so here we have on the right-hand side all the continents pretty much all together along the equator, whereas in the left-hand side we see them broken apart. So how will that play a role in global sea level? And if we just simply come up with the idea that, of course, on the left-hand side, we're more likely to find ice stored actually on the Earth's surface in the form of glaciers, where along the tropic areas, of course, we're not going to have ice. So if we look at the image or the globe on the left, the idea there is that's going to cause sea level to actually go down. So sea level will go down, as in this case on the left-hand side, the water is now stored on the Earth's surface rather than being in the ocean. So on the right-hand side, you're going to actually have, because of the position of the continents, you're going to have a higher sea level, or sea level is going to be at a higher elevation. Alright, time for some complex animations to showcase glaciers. Now let's pretend that we have a glacier here. So here we have a large mass of ice. So over time, this large mass of ice is going to get bigger. Why is it going to get bigger? Continuous snowfall. So one of the things is snowfall continues to occur. So you have high precipitation, but it's very, very, very cold. So that snow is going to accumulate, but as it accumulates on top of previous snowfall, previous layers, it's going to then compress the bottom. So one of the things you'll notice, you'll find at the bottom of a glacier, towards the bottom half, it's essentially solid ice. It's become compressed because of all that weight from all of that snow above it. And keep in mind that these suckers, especially continental glaciers, were in places 1 mile from the surface up. And so if you can just imagine seeing 1 mile from where you are up being nothing but a sheet of ice, of course that's going to do a lot of damage. And so this extremely massive, powerful eroder is going to cause landform change. It's going to cause the landform, in this case, to become compressed below it and actually create a depression. But we note this, that the glaciers, they've been retreating for a long, long time. And so one of the things to note is we see features that are left behind from these glaciers that are no longer. And so essentially we have these features that are now revealed once all that ice melts. That area that was once depressed by the huge weight of ice sheets during the most recent glacial period that depression starts to rise. And so currently Michigan, but also much of Canada, the crust is rising because no longer is that weight from that glacier overlying that area and causing the depression. This is a term that is called isostatic rebound. So it's what the experts call it. Glaciers are slightly moving rivers of ice, and so we have the kind of the same idea we talked about beforehand regarding erosion, transportation, deposition, but we think about these suckers have a whole lot of power. And so although they're slightly moving, because they're such massive structures, they're definitely going to do their damage. All glaciers, as I've mentioned before, are either advancing or retreating. What causes them to advance is just simply the increasing weight of continuous snowfall up there in the zone of accumulation is going to then cause the weight to then go either outward or forward based on what type of glacier it is. And so the simple idea is if I had just a big pile of pizza dough and I put my weight on top of that pizza dough, what would happen? That pizza dough would spread outward in all different directions. A nice simple way to understand and relate to this whole idea of increasing weight on the top is going to cause the flow to go outward from that area. And so it originates as snow on land, and then the stress combined with the weight and gravity then causes the flow to go either forward or outward. So we have very much a characteristic as far as at the bottom, a plastic-like substance. Glaciers move downhill because the ice is not strong enough to support its own weight, especially against the pull of gravity. And so we have this idea of increasing snowfall is going to cause this sucker to move outward, or in this case downhill. And so gravity combined with that weight does that. Further, where the base or the bottom of the glacier actually touches the underlying surface or bedrock, there's a bit of viscosity, or to maybe use a term you might know better, there's a bit of lubrication. And so imagine our good friend KY jelly. And so what that does is that offers a little bit of this fluid substance that allows the ice then to move slowly, but move further outward and forward. Glacier is the most powerful erosive force and also known as nature's bulldozer. And key to understanding is a process called abrasion. So the erosive process involves a couple characteristics, but the main one we're going to focus in on is abrasion. Simple idea here is moving ice. What it does is it plucks away debris and then carries it. So we have this initial plucking away of these large, sharp, angular rocks, and we'll showcase this in a following animation. Over time, those debris, those bits and pieces that have been plucked away, are moved to the front of the glacier. It very much acts like a conveyor belt, which moves from the rear to the front. So the origins of a glacier to the frontal edge of the glacial boundary. And so we see this idea of this debris being carried to the front, and it's carried to the front typically down there in that lower level, what I talked about, where we have a little bit of viscosity and lubrication. Further, the idea here is the debris brought to the glacial's front. Key here is you also have kind of a smoothing of the surface. So when we understand the U-shaped characteristic of a glacial valley, key to understanding is the role of abrasion as far as smoothing, instead of a V-shape like we talked about with rivers, smoothing it because of the weight, but also because of the other bits and pieces rubbing across the surface and smoothing it, so essentially polishing it. So imagine if you just rub rocks together for a long, long time, eventually they're going to be quite smooth because of the abrasion that's occurring. Further, when a glacier melts and is eroded, we have what we call unsorted sediments that are deposited at the mouth or the front of a glacier. We're going to call this a moraine. There's different types of moraines, but the idea here is we have deposition, so transportation and then eventually deposition. What do I mean by an unsorted? The idea is pretty much everything is just dropped in place. There is no layering. There is no specific patterns as far as finding a certain characteristic like silt, then clay, then gravel, and certain layers. No. It's just completely unsorted, just dropped in place. A key characteristic of what we'll find at the end or the glacial boundary where a glacier stops is this deposition. In the place where a glacier forms, the snow and ice accumulates in an area without any melting processes, and that's why it accumulates. If there was melting processes, it wouldn't accumulate, and we call this upper level the zone of accumulation. Then we have this other area that's separated, and separated by what we call the equilibrium line. So this red line would symbolize the equilibrium line. Simple idea here is the amount of accumulation, so snowfall and ice formation, is equal to the amount of melting. And so in other words, the losses of ice and snow are balanced out by the amount of accumulation. Down in the bottom at the zone of ablation, here we see increased evaporation and melting exceed the amount of snowfall. And so here we're going to find more of the melting. And so we see these different characteristics in these two different zones. In this image here for Mount Rainier, we can see at the top, we can see the zone of accumulation, and at the bottom we can see more of the zone of ablation. And so one of the things you note first off is this simply the color. And so here we've got freshly packed snow at the top, whereas at the bottom you're going to get a little bit more melting, but you're also going to get sediments and bits and pieces of rock that's actually been plucked away and because of abrasion been moved down to the front and deposited down here towards the bottom of this slope. Here we see a place in Wyoming where we can clearly see that equilibrium line. We can see where we have the zone of accumulation to the right or up the slope, and then of course the zone of ablation down at the bottom. Here we can see glacial polish and the whole idea of abrasion. So a glacier has moved across this area and smoothed it out quite considerably, almost to the point it looks like pavement, in which a human actually created this super flat surface. No, this was actually a glacier, so you can see that polish. What the arrows indicate is this glacier, because of the streaks that were left in the rock, either went, in this case, up or down based on its direction of its flow. Here we can see evidence of plucking. This massive large chunk of boulder to our right has been plucked away a long time ago. But one thing to know is when glaciers melt, essentially everything they carry, they just drop in place. So in this case, this big, huge angular rock to our right was brought by a previous glacier that was previously here in this area, but then subsequently dropped here. And so this is good evidence of plucking, what I've talked about beforehand. Two key types of glaciers. We're going to talk about mountain glaciers next, but here in Indiana we're overwhelmingly affected by continental glaciers and their various historical eras that have come through this area.